In Lesson 4, we will look at the FPGA implementation of the ADA 2.11 application framework. Specifically, we will go over a top-level overview of the FPGA code, go over some basics of FPGA programming, and then go into details on the FPGA implementation of the ADA 2.11 physical layer and lower MAC. In Section A, we will do an overview of the FPGA top level. This is what the top level of the FPGA code looks like for the ADA 2.11 application framework. As you can see, there are 4 main loops in this code. When we're on the FPGA, each of these blue loops is called a clock-driven logic loop or a clock domain, because each loop is going to be running at a different clock rate. If we actually look at what these different loops do, we can see that the loop at the top performs the MAC TX and the MAC RX functionality. Again, this functionality is implemented on the FPGA because it is necessary to complete timing. The loop below is the Phi TX and the Phi RX. The loop in the bottom left is the ADA 2.11 registers and FIFOs. And the loop on the bottom right is register bus and required controls and indicators. You can see with color coding that the green loop in the bottom right is for hardware-specific functionality, such as for a USRP Rio 160 MHz bandwidth hardware, and you usually won't have to touch this loop. The blue loops are the ADA 2.11 specific functionality, and we will go over these in the next few slides. First, in Section B, we will go over basics of FPGA programming. We will specifically cover transferring data between the host and the FPGA. We will cover the FPGA design language, and we will cover clock-driven logic. When transferring data between the host and the FPGA, there are 2 primary methods to do so that we will review. The first is using controls and indicators. These are slow and only provide the latest information. On the FPGA, what this looks like are controls and indicators that are in the code. In this case, operation select would be a control that is read by the FPGA from the host, and loop iteration would be data that is read by the host from the FPGA. In terms of what this looks like on the host would have a read-write FPGA control as shown on the slide. In this control, you can specify which control you want to write to on the FPGA or which indicator you want to write from. The controls and indicator methodology is used for passing control data to the FPGA, such as the MCS, or status data back up to the host. This type of information is very amenable for a slower transfer speed that only provides the latest information. The second methodology is by using direct memory access FIFOs. Direct memory access FIFOs, or DMA FIFOs, enable transfer of memory straight from memory on the FPGA to memory on the host without using up CPU resources. Therefore, DMA FIFOs are very fast and transfer all data until the FIFO overflows. DMA FIFOs come in 2 flavors: host to target, which we abbreviate as H to T, and target to host, which we abbreviate as T to H. On the FPGA, there are FIFO read and write nodes, which are these blue nodes shown on the slide. For each of these nodes, they have an input which specifies which FIFO is being read from or which FIFO is being written to. On the host, there are similarly DMA FIFO read and write nodes, which are these yellow nodes. In the properties for each of these nodes, you specify which FIFO you're reading from or writing to. DMA FIFOs are used for payload data to the FPGA, channel status to the host, or spectrum displays to the host. In other words, any data where you want to be transferring it fast and losslessly. When actually programming the FPGA, there are 3 different design language options in LabVIEW Communications. These are covered in more detail in the guided helps and tutorials in LabVIEW Communications, which you can access by going to the Learning tab at the top and then looking at the examples and the guided tutorials under the Learning tab. These are also covered in more detail in the LabVIEW Communications Customer Education course in lessons 6, 7, and 8. But at a high level, the three options are the multivariate diagram, the optimized FPGA VI, and clock-driven logic. The multivariate diagram and optimized FPGA VI are both higher-level design languages. In both cases, the idea is that you express an algorithm in a more intuitive way and let the compiler handle the FPGA-related details. For example, in the multivariate diagram, this is a high-level design language that is intended for algorithms centered around streaming operations. The multivariate diagram automatically handles the flow control of your algorithm, such as the pipelining and handshaking. The optimized FPGA VI is a model of computation that allows you to use for loops to program the FPGA. This allows you to express very highly parallelized algorithms very simply and also implement different things like array manipulations or state machines. The optimized FPGA VI will then automatically unroll for loops for you and automatically place feedback nodes in the code. Clock-driven logic is the lowest level design language in LabVIEW Communications. This is optimized for high performance and low resource usage algorithms through manual optimizations. And this is what the application frameworks are written in to properly be able to maximize the capabilities of the FPGA. In conclusion, you should try to use the right tool depending on the type of algorithm you will implement. Because the application framework is written in clock-driven logic, we will spend a little bit more time on some fundamentals of clock-driven logic. So where can clock-driven logic be used? Clock-driven logic is an FPGA design language. It can be used inside a clock-driven logic document, or a .gcdl, or inside the top-level VI on the FPGA inside a clock-driven loop. In both cases, the code will live on your USRP or FlexRIO FPGA target. In terms of the supported and unsupported data types and operations, in clock-driven logic, integers, fixed points, and complex fixed points are supported, in addition to Booleans, one-dimensional arrays with fixed sizes, and clusters, though the one-dimensional array functionality will increase to multi-dimensional arrays in future versions of LabVIEW Communications. You can also read from and write to FIFOs, both to the host and from the host, and between clock-driven loops. There's arithmetic functions, high throughput math optimized for low latency algorithms, Boolean operations, Xilinx IP blocks, and case structures so you can implement state machine-like logic. The FPGA code does not support floating point code and does not yet support multi-dimensional arrays. Note that in clock-driven logic, there also are no for loops and while loops, though in the optimized FPGA VI, you can use for loops. Besides algorithm functionality, a very important concept to understand with clock-driven logic is what is called the critical path. This is rooted in the fact that the logic in the diagram will execute in one clock cycle. In other words, all of the code within one clock-driven loop must execute once in a clock cycle. If the FPGA compiler will fail to meet this desired timing, the logical path is too long. In other words, if there's too much sequential code for the compiler to be able to complete it in one clock cycle, then you will have a critical path which is too long. To fix this, one will insert feedback nodes or shift registers to help relax timing constraints. This is called pipelining. However, as we will talk about in the next slides, each pipeline stage introduces latency. Now, another important concept to cover, especially given our conversations on pipelining, is throughput and latency on the FPGA. These are two very related but different concepts. Throughput is defined by how often data is outputted. In other words, how many clock cycles does it take for an output to be received on a block? The latency, however, corresponds to how long it takes between the first input and the first output for a function. So in the example at the top, we see that we get an input on clock cycle tick 1, and then it takes until clock cycle tick 2 for the first output. However, after that, we receive an output every clock cycle. Therefore, the latency is going to be 2, but the throughput is going to be 1. In the example at the bottom, we can see that we again get data in on clock cycle 1, but now it takes 3 clock cycles for the first output. Also, we can see that we get data only once every 2 clock cycles. Therefore, we have a latency of 3 and a throughput of half. Another fundamental concept in clock-driven logic and in FPGA programming is called handshaking. Handshaking is important because while every single block might execute once every clock cycle, every single block may not actually produce a valid output every clock cycle, as we saw in the previous slide. Therefore, there needs to be some form of flow control so that blocks can communicate to each other and only valid data can be processed and outputted. The two different manifestations of handshaking are 2-wire handshaking and 4-wire handshaking. In 2-wire handshaking, upstream modules indicate if its output stream is valid to downstream modules. The downstream modules use this signal as an input. 4-wire handshaking looks a little bit more complex, where you add 2 additional wires. The additional wires are the downstream module indicates that it is ready to accept data, and the upstream module checks if the downstream module is ready to accept data. In terms of the difference between the two, for 2-wire handshaking, imagine this situation. The first function produces an output after 1 clock tick. The second function, however, takes 3 clock cycles to actually function. Now, the first block has no way to know that the second block takes 3 clock cycles in 2-wire handshaking because all the control wires just flow downstream. So the first block could be producing an output every single clock cycle, while the second function would only be able to accept an input every 3 clock cycles. Therefore, you as the designer have to actually implement the logic to ensure that the data gets properly processed and passed so that blocks are only using valid data and you don't lose valid data. So it requires a little bit more work, but it actually results in a simpler diagram and also less FPGA resources used because you have less control wires. 4-wire handshaking provides a level of simplicity because all the blocks are communicating with their upstream block to tell it, yes, I can actually accept data, or no, I'm still processing data and cannot accept data. This, however, complicates the diagram because there are more wires and also results in more FPGA resources used because of the excess of control wires. In summary, in 2-wire handshaking, the next module always needs to be ready to accept data, while in 4-wire handshaking, the next module tells when it is ready to accept data. In Section C, we will go over the details of the FPGA implementation. Specifically for the transmitter, we will go over symbol timing, bit processing, and IQ processing, and their implementations on the FPGA. And on the receiver, we will go over the packet detection, synchronization, IQ processing, and bit processing implementations on the FPGA. This is the block diagram for the transmitter. The TX data source from the host sends data, or the PPDU, to the TX MAC on the FPGA using the ICP mechanism. We will go into each of these blocks in a little bit more detail on the next slides. The first main block on the FPGA is in the TX MAC and is called Prepare MPDU. Here, the MAC prepares the MPDU packet, which will be sent eventually to the physical layer. The next main block in the TX MAC, again on the FPGA, is the 802.11 MAC TX block. Here, the MAC waits for the channel to be idle, handles the backoff, and finally passes the TX request to the PHY TX request handler block in the PHY. Then we are in the physical layer. In the TX PHY, there's the main block, TX bit processing. At a high level, TX bit processing encodes the LSIG and data fields, but we will look at this block in more detail on the next slide. This is the block diagram for the TX bit processing. This is contained in 802.11 TX bit processing.gcdl. The purpose of the TX bit processing module is to generate the signal fields and enqueue the PSDU into the data stream. This stream is then serialized, scrambled, encoded, punctured, and interleaved before it is passed to the XIQ processing block. The first module in the TX bit processing is the TX-PHY state machine. Then comes the data generator VI, which furthermore turns the PSDU into a sequence of service field, PSDU data, tail, and padding for the 802.11a format, or service field, PSDU data, padding, and tail for the 802.11ac format signal fields, according to the standard. After this downstream module is the bit serializer module, which converts data fields and PSDU data into 1 bit per cycle. At the start of this module, a FIFO, which we discussed earlier, is used to ensure that the module can process the incoming data rate. After bit serialization, scrambling, convolutional encoding, puncturing, and interleaving are applied. The scrambler and the encoder must be reset before the first bit of the data field is processed. A FIFO is used on the input of the module since the data rate is higher on the input. The interleaver applies the BCC interleaver operations to conclude this module. If we then go back to the high-level block diagram for the transmitter, we see that the next block that we want to look at is the XIQ Processing Block. The XIQ Processing Block appends different fields and performs OFDM modulation. We will look at this block in a little more detail on the next slide. This is what the block diagram of the XIQ Processing Block looks like. This code can be found inside the 802.11 XIQ Processing.gcdl. The purpose of the XIQ Processing module is to add the training fields and to convert the bits from the TX bit processing block into baseband IQ samples. The OFDM single trigger of the RF loop is used to clock the generation of the OFDM symbols. The create packet structure modules creates a timing structure, a field map, and the processing parameters that stay constant along the OFDM symbol, i.e. bandwidth, cyclic prefix length, channel duplication, channel rotation, and tone scaling factor. Note that the XIQ processing block has to start delivery of IQ data as soon as possible after the TX start request is triggered. Because the IFFT takes about half an OFDM symbol, the LSTF is pre-generated in the time domain and its IQ data is stored in a block RAM. For IFFT prescaling, it applies tone field scaling to ensure that the time domain power of VHT modulated fields does not exceed the time domain power of pre-VHT modulated fields. So each is summed over all transmit channels. The scaling factor is determined in the create packet structure module and depends on the bandwidth and field type. We will now go over the block diagram for the receiver. The data source block selects the source for the receiver. Data can be taken from the RF, from the TX baseband using internal loopback, or from the host by using a host-to-target FIFO. The stream always has a sample rate of 80 megasamples per second for all sources. The synchronization detects the packet start and compensates an estimated carrier frequency offset. In parallel, the power measurement block calculates the received signal power. The stream is given to the XIQ processing block, where the samples are transferred to the frequency domain. Then channel estimation, equalization, and phase tracking is done. The constellation with field assignment information is provided to the RX bit processing block. Inside this block, the modulation is reversed, the bits are de-interleaved, decoded using a Viterbi decoder, and descrambled. This bit stream is given to the RX-PHY state machine. This state machine interprets the signal fields such as LSIG, VHT SIG-A, and so on in the PPDU and generates control information for IQ processing, bit processing, and MAC. The PSDU, which can be MPDU or AMPDU, is removed from the bit stream and delivered to the MAC as unsigned bytes. The MAC interprets the header information of the PSDU and transfers data to the host application using the LabVIEW target-to-host interface. So this is the high-level block diagram and how it's implemented on the FPGA for the receiver. We will go into each of these blocks in more detail now. This is a block diagram of the power measurement block in the receiver. This calculates the baseband signal power and the RF input power. It does so with these 4 blocks. There's a calculate signal power block, logarithm base 10, then an RF input power calculation, where it also gets in power calibration offset and RF gain, and then CCA energy, where it gets input from the host of CCA energy detection threshold. The outputs from this block are whether or not a CC energy is detected above the threshold, the RF input power, and also the baseband power. This is now the block of the automatic gain control state machine in the receiver. The AGC is used to ensure that the operating point of the system keeps in an optimum range. It is able to apply RX RF input gain values from 0 to 31 dB. In the state idle, the maximum possible gain value, 31.5 dB, could be applied to make sure that very low-powered incoming packets won't be missed. When the measured power exceeds a threshold level that can be configured from the host, the AGC waits for a second power measurement. This second value will be used to determine the applied gain for the current packet based on a host configurable mapping table. In the current implementation, the AGC is able to apply 4 different gain levels: 0 dB, 10.5 dB, 21 dB, or the maximum value of 31.5 dB. If the gain value is changed within a valid frame, the frame would be corrupted. To mitigate that, the applied gain will be locked after receiving a packet start signal from the synchronization module. This lock will be released after the end of the frame is detected. Now let's go into the synchronization block. This is the block diagram for the receiver synchronization. This can be found inside 802.11 synchronization.gcdl. This is implemented in 2 parallel paths to minimize latency. The upper path uses the package start sample index and estimates the carrier frequency offset. The lower path is the main data path, where it compensates for carrier frequency offset and generates the packet start pulse. For testing purposes, there is a bypass for the synchronization block where the packet start index can be given from the host. This path is not included in this figure, but you can use this bypass in combination with the RX samples from the host or internal loopback to characterize the RX baseband without the impact of synchronization algorithms. The next block that we will look at is the XIQ Processing Block, which is in the RX physical layer. This is the block diagram for the receiver XIQ Processing Block. This code can be found within 802.11 XIQ Processing.gcdl. The receiver XIQ Processing Block's purpose is to restore the transmitted IQ constellation. The sample timing generation module gets samples from the synchronization module along with the packet start index. The control information is carried by the sample timing cluster, which contains the following elements: the OFDM symbol index, the sample index with OFDM symbol 0 to 319, the packet start flag, the OFDM symbol start flag, and a valid flag. The sample index is used by the cyclic prefix removal module to invalidate the first 64 samples of each OFDM symbol. The demapper block aligns 2 control information clusters with the data stream. The first cluster is the subcarrier timing cluster, which includes the OFDM symbol index, the subcarrier index from 0 to 255, the frequency offset index, the OFDM symbol start flag, and the valid flag. The second control information cluster is the field map. This cluster is made up of booleans, and each boolean represents one field of the 802.11 packet structure, such as LSIG, LFTF, VHT SIG-A, pilot subcarrier, or data subcarrier. The channel estimation is computed using the second LLTF OFDM symbol for 802.11a and VHT LTF for 802.11ac. And the channel estimation block is implemented in a parallel path to minimize latency to the data path. Next, we will go over the RX bit processing block. This is the block diagram for the receiver RX bit processing module. This can be found in the 802.11 RX bit processing.gcdl block. The RX bit processing chain deinterleaves, decodes, and descrambles the data. It provides the receive bits to the RX PHY state machine and the PSDU bytes to the Mac. In the packet termination module, it passes all samples that have OFDM symbol indices in the subcarrier timing cluster below the value given from the RX PHY state machine. Passing only these samples ensures that the packet end is correctly processed. If you abort the current packet reception, this module terminates all IQ data by setting the last OFDM symbol index to 0. In the align configuration module, it has two functions. The first is to align the bit processing configuration cluster from the RX PHY state machine with the start of a new OFDM symbol. The second function of the alignment configuration module is to filter non-coded fields for downstream modules. It uses the field map provided by the XIQ processing chain. The deinterleaver module reverts the BCC interleaver operations. The depuncture module converts the incoming bit stolen data sequence to bit inserted data sequence. Each bit gets a puncturing flag attached depending on whether it was transmitted or left out. The descrambler module processes the bits at the output of the decoder. If the scrambler is disabled, the input bits are bypassed to the output. Then the output is transmitted to the RX PHY state machine. Before sending to the Mac, the bit stream is filtered by the PSDU masking module. The service tail and pad fields are removed, and the bits are concatenated to bytes. The length of the PSDU is given by the configuration, and padding bits are removed. Next, we will go over the RX PHY state machine. The RX PHY state machine provides the configuration for RXIQ and RX bit processing modules and generates indications for the Mac. Notice that the synchronization is controlled indirectly by the state machine. The RX end indication is used to rearm the synchronization. The word timing in this diagram refers to the time stamp when the last sample of the packet was received, which is included in the PHY RX end indication. This code can be found in the 802.11 RX PHY state machine.gcdl. Next, we will go over the Mac RX block. This is the block diagram for the 802.11 receiver Mac RX block. This code can be found inside 802.11 macrx.gcdl. There are 5 main blocks here. This block receives the PHY CCA indication message, the PSDU data, the PHY RX start indication message, and the PHY RX end indication message. The first block is the AMPDU frame validation, and then the MPDU validation. This block then goes to the channel state block in parallel, and the MPDU recognize block, and then finally the MPDU filter. The outputs from this block are the channel state indication, the RX indication, which is an ICP SDU, and MPDU generation request flag. This is what the actual CDL code looks like for the 802.11 Mac RX code. Here you can see we have the first block, which is the AMPDU frame validation, which is simply a sub GCDL. Then we have the MPDU validation, then channel state, MPDU recognition, and then in parallel the MPDU filter, and then also Mac RX statistics. Here we can see the wires that actually show the flow of data, where we have a few clusters that come in addition to the Mac device address, which is an array of integers, and the PSDU, which is an integer. And then we also have our green flow control wires or handshaking wires going from block to block. In exercise 4.1, we will go and understand the 5-frame structure. For this exercise, if you haven't already opened it, open up the ADA21 project, open the folder USRP Rio in the Files pane, and then open ADA21 FPGA sta.gvi. This is going to be the station FPGA code. Go to the diagram and locate the ADA21 XIQ Processing.gcdl block in the TX and RX loop. If you remember, this is the second loop from the top. Then locate within this block ADA21 create package structure.gcdl. Then inside that block, you will notice the subblock ADA21 field mapper.gcdl and open that. Finally, within that block, open ADA21 OFDM symbol type mapper.gcdl. Inside that block, use it to understand how the 5-frame structure is created. What is the frame structure for ADA21A and ADA21AC? If you recall from earlier in the training, these are the different frame structures for ADA21A and AC. Hopefully, you were able to actually parse this out from the block that we looked at on the previous slide. Note that if you wanted to, you could completely change this. This is just the default behavior out of the box, but this source code is yours to modify if needed. Now let's move on to exercise 4.2. In this block, let's understand the MAC frame structure. Okay, for this exercise, open up ADA21 FPGA sta.gvi unless it's still open. This is found in the USRP Rio folder in the Files pane. To look at the MAC frame structure, locate ADA21 prepare mpdu.gcdl in the MAC loop, which is the loop at the top. Locate ADA21 MAC frame header generator.gcdl inside this block, and open that up. From this block, understand how the MAC package structure is created. A question to ask is, what is the difference between the data and the ACK packets in the application framework? Also, to look at the data source for MAC fields, locate again, prepare mpdu.gcdl in the MAC loop, and within this, again, look at ADA21 MAC frame header generator.gcdl. From this block, understand the state machine which interprets the incoming data. What is the resulting package structure? How do you write the host G code for providing the data? And then compare this with the ADA21 sendtx icp.gvi. This is the solution to the MAC frame structure. In terms of the data frame, there's a frame control field, duration field, address field 1, 2, and 3, a sequence control field, and then an address field 4. Instead, however, the ACK frame has just a frame control field, a duration field, and only address field 1.